let's go ahead and get started talking about that. Once the slides decide they want to actually load, there we go. All right, so as I said, this section is going to look at a couple of different things. The concept of resistance, Ohm's law, which is tied to resistance, and also the idea of black body radiation. And what we're going to do is kind of base the whole thing around light bulbs, because light bulbs are something that we are all familiar with, and we can kind of deal with how they work. They're relatively simple. So it'll help us to picture all of these concepts and kind of tie them all together. So let's think about light bulbs a little bit first to start with. We know that it's important to close a circuit so that the current actually gets forced through the bulb filament to make it work. We've talked about that a little bit already. You know, when we had the light bulb and the batteries and so forth, if you didn't actually complete the circuit with the wire, then it wouldn't light up. So we've already mentioned that a little bit. And we'll talk more about those filaments and what's actually happening inside them in a little bit. The more current that goes through, the brighter the bulb will be. Seems to make sense that if we give it more electricity, then you're going to get more energy out as a result. Also, the higher the voltage, the brighter the bulb, because the voltage is, we can kind of think of as like the potential, it's the driving force behind the electrical current. So if we have a higher voltage, it's going to be forcing more current through. And then power is going to be equal to voltage times current, so obviously increasing either of those increases the overall power. So this is the energy transfer we're talking about from the chemical potential energy in the bulb to the radiant energy that is what we're hoping to get from the bulb, the whole reason that we are using the bulb in the first place. All right, so looking at a bulb, here are the basics of the design. Down here at the bottom are where we have our electrical contacts. So that is where the circuit is going to basically be making its connections, which allow it to form the complete loop that it needs. The main functional part of the bulb is the filament that's in it. That's the key to making it work. And that is in a traditional incandescent light bulb that is done with tungsten, which is one of the reasons why we are trying to move away from those bulbs nowadays, because tungsten is getting fairly rare. It's hard to find on the planet anymore. It's not easy to work with either. And besides that, these bulbs are extremely inefficient. They're probably about the most inefficient devices that we commonly use. I think they're only somewhere in the neighborhood of between 3 and 5% efficient. So, you know, the vast majority of the energy you're putting in them is being wasted. Most of it going to heat, as anybody who's ever tried to change a light bulb that's been on for a while knows. You know how hot they get. That's all the wasted energy that's being given off. We're trying to produce radiant energy, and you're producing a good portion of heat instead. And then obviously the bulb is all sealed up and there is gas that's contained inside of there. That was the other trick to actually making a light bulb work in the first place, was finding the right combination of filament and gas to give it enough lifespan to make it worthwhile. That's why it took, I think they said it was several thousand trials in order to actually get the right combination when Edison was working on the light bulb. So if we look at a typical 120 watt light bulb, at the 120 volts that we are getting for our houses, it means it must be conducting 1 amp because the power is equal to the voltage times the current, as we mentioned before. And that means that the bulb is giving resistance of about 120 ohms, because this is the new law that we're going to get into. So we'll see more about what all of that means later on. But what's actually going on inside the bulb is going to be very much connected to that concept of resistance. That's why we're kind of focusing on the bulbs to present it. So the filament in the bulb is really just a very, very thin wire, and the current is flowing through that wire from one end to the other. What the filament is doing is providing resistance to the current because it is so thin. And basically what's happening is the electrons, as they're trying to move through there, have a lot of things in their way. It's not a very big pathway. They have to kind of squeeze their way through. So they're banging into things, and that's producing a lot of heat. It's very similar to how we get friction whenever two surfaces are rubbing together. This time the current's trying to flow through there, and there's just not that much room, so it's creating collisions. And all of that heat causes the filament to get hot, and eventually it will get hot enough that it will start to emit light. And that's when we get the glow from the light bulb. So the filament gets red hot and gives off visible light. Okay, a little bit more about things emitting light. All objects are going to emit light to some degree. Most of the light that we see is actually reflected light, because it's light that is bouncing off of the surfaces of things. So the color and intensity of the emitted radiation that we see coming from objects is going to depend on their temperature. And of course, our eyes are going to be optimized to detect light that is emitted by the sun, because that's what we've evolved to deal with. The sun is producing our light that we're accustomed to here, so our eyes are adapted to that. And that's how, for most of our history, we saw things, was all via reflected sunlight. In the past, our ancestors were not looking at things under light bulbs or staring at TV or computer screens or things like that, like we are all the time now. So we do make these devices now which have their own artificial light sources, and obviously ideally what we do is we try to make them give off the similar type of light as the sun does, because if you do that, our eyes are able to deal with it much better. It's something that we've gotten better at in recent years, because the computer monitors and stuff that we had in the past were very harsh light, and it was very hard to work with them all day long because our eyes just weren't adapted to it. So they've actually improved them a lot, although it's still hard to look at a monitor all day long, as I'm sure all of you guys who have been doing that for school all year at home realize. Okay, this is just a comparison of the type of colors given off by objects. So all of us who have a temperature of in roughly the 30 degrees Celsius range, we give off infrared radiation. So it's invisible to our eyes. It is detectable by some animals, but we can't see it. And that is right below the visible spectrum. something like a heat lamp has a temperature of approximately 500 Celsius, and that one would glow like a dull reddish color. A candle flame can get up to about 1700 Celsius, and that one will be a dim orange color. The filament in a regular light bulb can get up to about 2500 Celsius, and that one will glow yellowish. And then the sun's surface is approximately 5500 Celsius. That's at the very surface of the sun. The interior of the sun gets into the millions of degrees, so it's a huge difference between the surface and the interior. But that, at that point, is a brilliant white color. Basically what happens is that the cooler something is, the more reddish it appears. The warmer it is, the more towards the blue end of the spectrum it will appear. And then obviously the radiation becomes more intense as well because it's more energetic. So this is a diagram that's known as a black body spectrum, showing you the optimal wavelengths given off by different objects. This is a different view of that's based on a logarithmic scale, so it's just a modified version of the other graph. But you can see some of the things are labeled on here. So the black body radiation curve at the sun's temperature, this is where visible radiant light would be. This would be an incandescent light bulb over here. This is what you would see for the Earth, etc. So if you were looking at the Earth from space, that's what you would see. So that's just showing you the various ranges on there. Now let's take a minute then and think about that whole idea of black body. And what you're probably thinking is a lot of those things aren't black. And what black in this context means is that it's that the reflected light isn't important. So if you think about something like the hot charcoal on a grill, it's glowing bright orange when it's hot, but in reality we know that they're actually black. Not everything is truly black, but if you look at it on a small enough scale where it's actually interacting with infrared wavelengths, then it's actually kind of surprising how black things actually are there. So our skin at that scale is 90% black, which means that it's absorbing most of the light and only radiating off a small amount. Even something like pure white paint at that scale is practically black. So that's where the term actually comes from. Metals will actually still be shiny though, so that's an important difference because that has to do with their metallic characteristic and their atomic structures. So even at that scale, they still have that shininess to them. The property is called emissivity, and it gets into a pretty complex equation here, as you can see, which we're not going to deal with. But it's just important to know that it is looking at a scale between 0, where things are perfectly shiny, they're radiating all of the energy back, and 1, which is perfectly black, where they're absorbing all of the energy. And there's nothing that we know of, at least, that is perfectly black. But a black body, whenever they talk about that, is something that we're assuming is absorbing, close to all of the energy. The only thing that in the universe that we know of that's really close to truly being a black body would be a black hole. And even they do radiate some energy because they're absorbing so much that they can't pull it all in. They're too small an area to pull on all that they absorb, so they radiate a lot back out. So think about this in terms of why do we use aluminum foil whenever you're cooking something. When you wrap it in aluminum foil, what you're doing is you're causing that energy to radiate back out of it and bounce back to the food and cook the food faster. All right, so let's go back to our light bulbs then and think about what limits they have on how long they last. So we said that we have a tungsten filament in there that's really thin, and we're heating it up. When we heat it up, what's going to happen is some of the tungsten atoms are going to be driven off. They're going to get so hot that they'll be able to escape the wire. So because it is heat, it's causing vibrations in the atoms, and those violent vibrations are going to occasionally eject atoms, especially when you're dealing with a very thin piece to begin with. So you have a trade-off between how hot the temperature can get and how long the filament's going to last. If it's brighter and whiter, it means that it is hotter, so that means that the vibrations are more vigorous, and therefore there'll be more atoms which are booted out. Some of the newer light bulbs, like the halogen bulbs, are actually able to last a lot longer because they will be able to take some of those atoms that are being booted out and get them to redeposit back onto the filament. So they're kind of being recycled over and over, and therefore they can end up burning hotter and lasting longer at the same time. They're also, as a result, more expensive, but it's one of those you get what you pay for situations. Eventually the filament does burn out. No matter what type of bulb it is, it's going to last for a finite time anyway. Once that happens, that means that there's a break there. The current can no longer flow, and therefore we no longer have light. And we already mentioned about the efficiency of incandescent light bulbs, which is extremely low. As a matter of fact, they were already supposed to have been off the market about a decade ago, but they got kind of a stay of execution. Some of the people in the government were protesting it and claiming that we, don't take our light bulbs away from us, that kind of thing. And they made protests about the other bulbs having, dangerous materials in them and all this kind of stuff. So whatever the case is, they've hung around longer than they were intended to. Is that your foot? Okay. Thought that was the beginning of a fire alarm. I'm like, oh, we just did that. Okay, so that's going to bring us into our discussion of Ohm's law here then, which is our main point for today. And that'll also get us into talking about circuits, which we will save and look at next week. But the concept of Ohm's law is a really simple equation here, just V equals IR, which is voltage is equal to current times resistance. So voltage and current we've already talked about, we've seen those before. Resistance is the new idea, so that's the one that we have to look at. And it's exactly what it sounds like. Resistance is going to be how much something is going to impede the flow of current moving through it. It's measured in this funky looking unit known as ohms. That is a Greek letter omega, I believe it is the symbol for it. So at this point, we're really running low on other symbols, so we're digging deep into the Greek alphabet for them. So think about what we talked about before with the bulb filament and how it's kind of working like, the bumper cars at Cedar Point, bouncing off of each other and everything like that. Electrons are bouncing off of the lattice work structure of the atoms in the metal that they're traveling through. And because of that, they're blocking the flow of current, so they're providing a resistance. So that's basically, in a nutshell, what is going on with resistance. So here's a couple ways to think about what's going on with Ohm's law. So if you have a current running through a resistance, there will be a voltage drop. So you can look at it in terms of the change in voltage is equal to the current times the resistance. So that's one way that you can measure it, and there are actually devices that you can hook up to either side of a part of a circuit, and you can measure the voltage drop across them to see what effect the resistance is having. Other ways of looking at it is when you put a voltage across a resistor, the current will flow through that flows through the resistor is going to be equal to the voltage divided by the resistance. So that's just rearranging the law. Or you can look at it in terms of resistance. So the resistance is equal to the voltage divided by the current. So just taking the basic equation and reworking it different ways. But Ohm's law is going to really help us to understand how current is going to decide to split up whenever there are junctions. And the junctions are going to be important when we're looking at circuits, because that will determine the hows and whys of how we design circuits, is based on where the current's going to flow. And so that's all based around this idea of Ohm's law. So it's a pretty simple law, but it's a really important one. So we'll look at a couple of examples of this here today, and then save most of it for next week. So here's a really simple circuit we have. So we have our battery power source here, and we have a couple of bulbs that are hooked up, and you can see there's just one loop for it to go through. So this is a series circuit, the simpler type of circuit that we have. And if we add more bulbs in series, it adds resistance to the current, so the current flows, so there's less current that flows through. Each of these bulbs is providing resistance because each of them has a filament that it has to go through, and the electrons have to bang their way through. So the question here is, which bulb is brighter and why, if we have them hooked up like this? And in this case, there's only one current that's flowing. It only has one path that's going through. So it's going through both bulbs. So both of them will be equal brightness. If you think about it, if you exchange the bulbs, if we switch A and B around, it's not going to cause any impact because the bulbs are identical to each other. So it's not going to make any difference one way or the other. So in this case, the bulbs will be equal brightness, but if we have more of them, then every time we add more of them, it will add resistance, so there'll be less current flowing. So by adding more bulbs, each would get dimmer. They'd still be the same brightness as each other, but they'd be dimmer as a whole. So 3 would be dimmer than 2 would, 4 would be dimmer than 3, etc. Okay, and this is a very complex one, obviously, but that's a preview of some of the things that we'll get into next week with it. So we are going to wrap it up with that here for today. I'm not going to give you anything new to worry about today. We'll save the stuff for next week. And we'll do some practice with Ohm's law and some practice with circuits next week. And I also will give you the stuff about the final project, so you'll be able to start thinking about that next week, and we'll probably start working on it the week after that, is what I'm guessing. So go ahead, use the rest of the time today to finish up any of the other assignments that you need to finish up on. And if you're good with those, then you're golden. You don't have anything to worry about over the weekend. Do keep in mind that interms are coming out Monday, so if you have anything you want to get on in the grade book for interim, send it to me by the end of today so I can get it in over the weekend.